This is the pre-lab talk for experiment number 4 for Chem 120 lab, absorption spectra and color. The goals of this experiment are to explore the use of absorption spectroscopy in monitoring a species that's in solution. We will also explore the relationship between the color of a solution and its absorption spectrum. This will require us to use a new piece of equipment, the SpectraVis Plus spectrometer, to measure absorption spectra of different solutions. For today's safety pause, we note the hazards associated with potassium thiocyanate, or KSCN. KSCN poses a hazard when mixed with other chemicals, such as acids, where it can end up producing a toxic gas. Therefore, care should be taken when using KSCN. For this lab, all waste will be collected in a special waste bottle. Nothing will be poured down the drain. And as always, we want to make sure that we goggle it and wear our flame-resistant lab coats. Absorption spectra and spectroscopy are things that are not discussed very much in lecture. However, it is such an important tool in chemistry, we do want to cover it in a laboratory where it's more likely used. Spectroscopy is actually the study of how light interacts with matter. What you might remember from lecture, especially in Gen Chem 1, is that the different wavelengths and frequencies of light make up what's known as the electromagnetic spectrum. The electromagnetic spectrum ranges from short wavelength high frequency light to long wavelength low frequency light, gamma rays to radio waves, respectively. Each part of the electromagnetic spectrum allows us to study a different aspect of matter. For example, if you've ever had or have heard of an MRI, that is a form of spectroscopy. In MRIs, or if we're just looking at molecules, NMR, we look at the interactions between atomic nuclei that have a spin, such as hydrogen, which is one of the main components of water, which make up the majority of your body. This is why MRIs are so useful in looking at and imaging different structures within the body. In this experiment, we're going to focus on visible light, since many of the samples that we'll be looking at have different colors. In visible spectroscopy, we focus on the absorption and transmission of light. Let's look at a simple example. If you shine white light, which composes all of the wavelengths of visible light, on a sample, some of that light is going to be absorbed by the sample, and some will be transmitted. As you can see in the picture, all the wavelengths of light go through the sample, and red, blue, and purple light are transmitted. The other wavelengths of light, or colors of light, are absorbed by the solution. The incident light coming from the source has a certain intensity that we'll call I sub 0, while the light that has gone through the solution has another intensity that we call ITR. We can quantify this light that is transmitted or absorbed by using what we call absorbance and transmittance. The transmittance, which is the ratio between the light that has gone through the sample and the light that came from the light source. Oftentimes we talk about the percent transmittance, which is taking the transmittance and multiplying it by 100%. This gives the percentage of light that has been transmitted by the solution. Finally, we can also quantify the absorbance of light, since the light that is transmitted is the light that has been absorbed by the sample. There's a logarithmic relationship between transmittance and absorbance. Absorbance is equal to the log of 1 over the transmittance. A solution that completely transmits the light has an absorbance that's pretty close to 0, while solutions that have high absorbance have very low transmittance. We can use these relationships to plot what is known as an absorption spectrum of a sample. Here's an absorption spectrum of the pink solution that we have in the pictures. In an absorption spectrum, we plot absorbance versus the wavelength of light. When you see a peak in an absorption spectra, such as the peak in this spectrum that occurs around 550 nanometers, this corresponds to light that is absorbed by the sample. Portions of the absorption spectra where the absorbance is very low or close to 0 represent wavelengths of light that are transmitted. In our absorption spectrum, we see that the light that it seems to be transmitted by the sample occur around between 400 and 450 nanometers, and also beyond 600 nanometers. This corresponds to blue and red light. Therefore, we can assume that the blue and red light that's transmitted is what reaches our eyes and gives us the apparent color of the solution. Therefore, the colors that we see come from light that is transmitted or reflected by different objects. We'll explore this more in this experiment. Let's look at a couple of procedural points that are important for this experiment. Many things will be discussed in the video. The picture on the right shows a Spectra Vis Plus, which you can see is essentially appears to be a black box. Our samples or solutions are put in little containers called cuvettes. The cuvettes we'll be using in this experiment have two faces. One face is a clear flat face, which accounts for two of the faces for the cuvette, and then the other two faces are ridged or fluted. It's very important to make sure that the light source is going through the clear sides and not the fluted sides. It is also important that when handling the cuvettes, that you handle them with mainly the ridge sides, and if possible, wearing gloves, since the oils on your skin can actually interfere with the collection of the spectrum. One of the things that can cause damage to the spectrometer is liquids getting into the spectrometer itself. To minimize this, the cuvette should only be filled about 2/3 to 3/4 of the way. And a plastic cap should be used to minimize the risk of spills. Before putting the cuvette in a spectrometer to record a spectrum, we'll also wipe down the sides of the cuvette using a chem wipe, which is a sensitive instrument wiper that will remove all fingerprints and excess liquid off the sides of the cuvette. Since the Spectra Vis Plus appears to be a black box, let's briefly talk about how it works. Inside the Spectra Vis Plus, there is a light source that, as we talked about before, will produce all wavelengths of visible light. This visible light will go through the solution that's in your cuvette. The light that is transmitted by the solution will then hit what's called a diffraction grating, which is a little piece of plastic or glass that has ridges in it. The ridges help to bend the transmitted light so that we can see the different wavelengths that make it up. These wavelengths of light will then hit a detector array that consists of 650 elements that help us to detect the different colors. This information will be sent to the computer and a spectrum will be collected. The Spectra of His Plus does need to be calibrated, which is something we didn't see very much in other pieces of equipment that we've used. To calibrate the Spectra of His Plus, we need to put in what we call a blank cuvette, which usually contains the solvent that the solutions are made of. For this experiment, we'll be using distilled water as our blank. Obtaining the spectrum is pretty easy. We'll just simply hit the collect button, and in about 2 seconds, the spectrum will appear on the screen. Usually you can keep collecting for a while, but the spectrum will not change unless something pretty drastic happens to your system. For example, if you accidentally take out the cuvette before finishing the collection of your spectrum. I hope you have fun learning about the ins and outs of how we perceive color and what that has to do with light that is absorbed and transmitted by solutions.